Okay. Yeah, hello. Welcome to week 9 of QDA, which is meeting number 8 and lecture number 7. That will continue to be confusing for the rest of the year. You can always feel free to put your comments and questions in chat as we go, and we'll try to address everything as it comes up. But anyway, we hope that your first assignment was not too painful. We're aiming to have feedback to you in 2 weeks on November 24th. That'll be the day of our final class meeting. It's the week before the multiple choice quiz. And that's going to be a review session where you can just ask questions about anything that's come up throughout the class to kind of help you prepare for assignment 2 and for the multiple choice test. So as a reminder, yeah, your final assignment will be due on December 9th. We definitely, we've been marking a lot of these so far. We've been trying to mark as quickly as we can so we can get you guys feedback. And in my opinion, it looks pretty good so far. I mean, the first assignments always have certain kind of characteristics in common, good and bad. And I've seen some good stuff this time. So good stuff all around. Hopefully you'll be as happy with your grade as I am. It never ends up being that way. I think I'm always a little more bright and cheerful about your grade than you end up being about it, because everyone thinks they always should be getting an A+. But I think these look good. I also want to thank everyone who completed the feedback form. I know some of you did, some of you didn't. That's all right. I was pleased to hear about the things that are working well in this class, and I got a lot of ideas about how to improve the class. So 2 kind of actionable items that I'll try to implement that I got in a few pieces of feedback were to try to use simple examples and try to use as simple language as I can. I'm terrible at that in general. I always use I use way too flowery of language all the time, and I'm sure that doesn't help you learn statistics. So please do stop me and ask me to restate things if I'm saying things in a confusing way. One note that I've been seeing from a lot of students in the feedback forums is that in terms of positives is that text resources have been really helpful to you. So that's things like textbook, but also my weekly code file comments, where in the practical and the R files, there's like lots of info in the comments, as well as my speaker notes. So if you download the PowerPoint version of my slides, that'll have the notes that I'm reading from right now. In fact, you could give the lecture along with me if you wanted to be really weird. You could read exactly what I'm reading. But people who have used those have said that those text resources have been helpful. I definitely encourage you to take advantage of those things if you're unsure about things, about technique that we use or a statistical concept. I also encourage you to make use of email and office hours if you're struggling with any particular concept or any specific part of our code. We've had our fair share of office hour meetings, but they've almost entirely been about the first assessment. They're not usually about like class content. So if there's something in particular in the class that you'd like to go over or get some extra help on, please do let us know, because when we don't hear from you, we just assume that things are going well, that you're understanding. So we don't really change things up. So do let us know if you ever want some extra help or extra resources on a particular concept. And also make use of your classmates in that way. I see a decent handful of the buddy groups have kind of taken conversation to WhatsApp. I don't necessarily like that happening, because then if there's like back channel conversations that are like kind of about the class, then I can't really get involved and help out. But also if there's conversations that like shouldn't be happening, I won't be seeing them. So make use of each other as resources, but maybe try to keep it on Brightspace for my benefit. Also, if your specific feedback is not being addressed either in what I'm saying now or in changes we make over the next few weeks, first thing I have to say is I'm sorry. We have had requests to spend more time on every different aspect of the class. People will say we need more time on statistical concepts, less on code. People will say more time on code, less on statistical concepts. People who say the order we do things in now is good. People who say the opposite order would be better. I can't really meet every piece of feedback without kind of contradicting other pieces of feedback. Likewise, I can't really add time to any part without taking away from something else. And the length of time that we spend in this class is outside of my control as a PhD student and a tutor. I am not UCD staff. I cannot request extra time to teach this class. Likewise, on that note, a handful of you have requested that more parts of this class would be better in person, or that we should have more in-person components to this class. Unfortunately, that is not what the school decided to do with the module this year. And like I said, yeah, I'm a PhD student, I'm a tutor. I can only work with what the school and the module coordinator have designed, but I don't have the power within the school to change the format of the module. I've made that feedback known to the module coordinator, to the heads of relevant degree programs. This is something that I saw a lot of this feedback, and I've tried to communicate it as best I can, but if you're wondering why I'm not doing anything to address it, I'm doing what I have power to do, but yeah, I'm a student like you. It's not a perfect situation for this module or for any module, but we as UCD students ourselves want to make sure that you as students have the best student experience possible. So please keep structural feedback like that coming, but also keep it coming towards the school in general, because those are the people who have the power to make those changes. Anyway, that's enough about me complaining why I can't fix everything. If you have any kind of more feedback or comments or questions, you can still use the feedback form, and you can always email me directly. Anyway, let's get into this week's statistical test. This week we have a new statistical test, the t-test. And this is always a very special lecture at UCD, our t-test lecture. It's a very special lecture because this statistical test was born right here in Dublin, in Kilmainham, at the Guinness Storehouse even. We will start our lecture with a research question and a hypothesis like usual, but then I will be telling you about the history of the t-test and then what it is used for. That'll help us see how we can use the t-test to test the hypothesis that we come up with. And as always, we'll try to end the lecture with info on how to report the results of a t-test and demonstrate how those results are used to answer our hypothesis. So let's flash back to week 2, the scientific method. We might, there's a couple of ways we can start the scientific method. I always use that circular diagram that there's kind of no beginning or end point, that it just all feeds into itself. But one place you can start in the scientific method is by making observations about the world and then using those observations to ask research questions. I make observations all the time when I'm out in the world. I'm almost always walking around. I don't drive a car. I don't cycle in Dublin much. I find it really scary that the cycle lanes are like shared with the bus lanes. And I try not to be too reliant on the buses or the Lewis. I'm just walking around constantly though. So I see a lot of different things about the world around me. I make a lot of observations. And one observation I tend to make is that there's a lot of cyclists that share the road with cars and that have to navigate crosswalks that people like me might be crossing. And I've noticed something out on my walk. I've noticed that sometimes the people who are riding their bikes don't completely obey the rules of the road. They try to fly across the crosswalk when it's meant to be my turn to safely cross, or maybe they make a turn directly into traffic when a car is kind of meant to have the right of way. And one thing I have observed while I'm out seeing these cyclists barreling into traffic is that a lot of the most dangerous decisions that cyclists make on the road occur when the cyclist is wearing headphones. So I make this observation that I think that people who wear headphones while they're cycling are worse at cycling. They're making more dangerous decisions. They're not following the rules of the road as well. And this observation might lead me to ask a few different research questions. So in the past few lectures, we talked about cross-sectional studies, where a research question might be asking about the association between two variables, the relationship between two variables, something like, is wearing headphones while cycling associated with dangerous cycling? But this week, I don't just want to ask about the association, I actually want to ask about the cause. My research question is, does wearing headphones while cycling cause people to be worse cyclists? And I'm asking this question about one variable causing another. So if you remember back to week 2 and week 3, when we have that format, when we have one variable causing another variable, the only way to test that relationship is with an experiment where we manipulate one variable and control the rest of the variables. So When we talk about a causal relationship, like we're doing this week, we need an experiment, we need an independent variable. So let's talk about how we might design an experiment to test our research question, to get at this idea of headphone wearing causing cycling issues. Yeah, yeah, definitely. I think that's it's shocking that it happens in the Netherlands. I associate the Dutch with being like borderline professional cyclists. I was always very scared when I had to walk across a cycling path there, because it seemed like if anyone was anywhere near me, they could just destroy me. So how would we design this experiment to test whether headphone wearing causes poor cycling? Well, we would want to see if headphones cause some change in the dependent variable of cycling ability. So we need headphone wearing, the headphone condition, whether you have headphones on or not, to be our independent variable. That's the thing that we are manipulating ourselves. We are assigning participants to either wear headphones or to not wear headphones. And the control group in this experiment would be people cycling around without headphones on. That way there's something to compare against. While our experimental group is our headphones group. They are the group of participants who will be listening to music on headphones while they cycle around. And they would cycle around the exact same cycling track, let's say. Again, in this example, we can imagine like I went to UCD, told them I wanted to use this experiment, and I wanted to run this experiment, and they told me you could use an entire parking lot and build a little closed cycling track with like pedestrians and with cars and stuff like that. Yeah, definitely. I think great idea for UXD, or if you take the HCI module next term, I think that's a good idea for like a design friction, headphones that turn off if they detect that you are cycling. So for our independent variable, we might want to measure how good or bad our participants are at cycling. Sorry, for our dependent variable, we want to measure how good or bad our participants are at cycling. We want to measure cycling quality. We could do this a few different ways. We could use like an objective measurement. We could like count how many times they bump into a car, or how many times they like touch a pedestrian. We could count how many seconds they spend outside of their lane, or how many centimeters they average outside of the center of the lane, or something like that. Or on the other hand, we could use a subjective measure. We could use an expert's rating. So we could have like a professional cyclist or a cycling coach or something, watch them cycle around and then rate them on a scale of 0 to 10, or I said in this case, 0 to 8, how good or bad the cycling was. And in this case, I don't really want people colliding into cars and pedestrians. So I think I'm going to go with a subjective measure, because I don't want to have a design that's like so dangerous that some people will be crashing a lot and others won't be. Instead, yeah, we'll just measure this subjectively. We'll have some judges, some expert judges rank them from 0 to 8. And for the task itself, yeah, we'll just have a closed course that we're building in the UCD parking lot. There'll be pedestrians and cars that kind of go through intersections at certain moments, like a car that maybe pulls into your lane unexpectedly. Little surprising moments like that in the track. I expect that since I have these surprising moments in my track, that my cyclists would do much better if they had a second time through the track. That if you experienced it once with headphones on and then experienced it again without headphones, or vice versa, you would just do so much better your second time, because all of those surprises would be in the same place, right? So for this reason, I'm going to choose a between subject study. I'm going to have each participant only go through the track one time in one condition or the other. That way they don't experience both conditions. They don't get the practice effect of knowing how the track's shaped and like where the surprises are, things like that. So I'm going to use a between subject study with an independent variable of cycling condition. That independent variable has 2 levels, headphones and control, and a dependent variable of cycling quality on a 0 to 8 subjective scale. So that's my experiment design. So let's formulate a hypothesis. As usual, we want to make sure our hypothesis is testable, specific, parsimonious, and falsifiable. We want this scientific hypothesis. We want to predict that there will be a significant difference between cycling conditions on cycling quality scores. That means our null hypothesis is the opposite, that there will be no significant difference between the cycling conditions in terms of cycling quality scores. So we have our experiment designed, we have our hypothesis. but we need an inferential statistic that we can use to evaluate that hypothesis. We need some statistical method to tell us whether our hypothesis is supported or rejected. And that is where the t-test comes in. T-tests are designed to measure the difference in a continuous variable between two groups, exactly two groups, not more than two, just two. But that's exactly what we have here. We have a continuous variable, cycling score, and we have two groups. We have our headphone condition and we have our control condition. So this is exactly what a t-test is designed to measure. When you see this question of differences between conditions or like differences between means, that's when you know that you should be using a t-test, and vice versa. If you're using a t-test, you know that you should be measuring the difference between two groups, the difference between two means. So let's get some history. And this is going to bring us back to Dublin of a century ago. This is early 1900s, Dublin. We're at the Guinness storehouse. Our main character is this man on the right, William Seeley Gossett. William Seeley Gossett is a new brewer. He was a brewer in London, and Guinness at the time was a British company, if you can believe it. I guess depending, yeah, we were very early in the 1900s, so I guess Ireland was still under British control. Anyway, William Seeley Gossett, a Brit, was the new experimental head of brewing at Guinness. That means not only was he the head of decisions on how Guinness would be brewed, but he was meant to make these decisions by using scientific experiments. His job is to design experiments to make brewing more efficient for Guinness. So lower cost beer at a higher quality. And Gossett notices that there's many different ways to brew beer. There's many different types of barley which can be used to make Guinness. And in this case, he identified many different varieties of barley that could be useful for making Guinness that all kind of had the same quality. They all tasted about the same. So William Seeley Gossett wonders which type of barley can he plant to get the best yield. If it doesn't matter which one you use, that they all kind of give you the same tasting beer, and the only difference between them is which one is most efficient, which one can harvest the most from a single kind of crop of that beer or of that barley. So Gossett ran an experiment. He planted a field of one type of barley, planted a field of another type of barley, and just measured how much barley each field yielded, or each plant in specific yielded. And he needed to compare those. He needed to do just the same sort of hypothesis testing that we're doing. So he wasn't a statistician by training, but he knew some statisticians. He knew Pearson and Fisher, who you might remember from a previous lecture. Those guys, I noted, big old racists. William Seeley Gossett, unproblematic king, possibly. I didn't see anything too controversial in his past, at least. But yeah, he was friends with Fisher and Pearson. He knew them from his university days. So he asked them for some advice with statistics, and he got some stats tips, but they weren't super interested in his barley question. So he decided to develop some statistics on his own, and he developed what is now known as the T distribution. It's a probability distribution, just like the normal distribution, that lets us estimate the mean for a population when we have a small sample from that population, and when the standard deviation of the population is not known. So this was a hugely important innovation for statistics. Means now Seeley Gossett could compare two means and assign a p-value to that comparison. In other words, if he observed the mean amount of barley that one of his crops yielded, and he observed the mean amount of barley that the other crop yielded, he could express a confidence interval for the true mean yield for each population. So he only needed to plant, a few crops of this one variety of barley. He didn't need millions and millions of samples. He just needed a small sample to make some estimate about the population mean for that crop, and likewise for the other crop. And with these two estimations for the population mean, he could also do a comparison and test whether or not they came from the same population. When Seeley Gossett invented the T distribution and the T test, there were some strange rules at Guinness. Guinness had previously had some of their scientists, their experimental brewers, going off and publishing papers under their own names, and then other breweries were stealing ideas for how to make beer. So they said, you can publish papers, but you cannot use your own name, you cannot mention beer, and you cannot mention Guinness. So Sealy-Gossett published this research under the name student. So you might see student's t-test or student's t-distribution. That's just Gossett's pseudonym. It may as well be called Gossett's t-test, but he published under the name student. And nowadays, if you go to the Guinness Storehouse, you can find a section in the museum dedicated to William Sealy-Gossett and his contribution to statistics. I definitely recommend doing that, just as an excuse to go check out the Guinness Storehouse museum experience and get a pint of Guinness while you're there. So this is our hero for today's lecture, William Sealy-Gossett, is Guinness Storehouse. So this is what the t distribution looks like, and it looks a lot like the normal distribution, but it's a little bit more pointy. It's a little bit more peaked at the top, and the tails are a bit flatter. The x-axis in this t distribution is the standard deviation, number of standard deviations of your sample. And the y-axis is probability of observing a sample with that mean. So if you have, and v is your degrees of freedom. So in other words, the sample size. And I'll get into finally a big discussion of what degrees of freedom really means, but it can basically be a proxy for sample size for the time being. You'll notice that the distribution gets more pointy as the sample size increases. So with a bigger sample, you can be more confident that your sample mean is close to your population mean, that it's less and less likely to observe a sample mean that's many standard deviations away from population mean. Since this is a probability function, you can use this distribution to make a confidence interval. So if you, let's say you had your Sealy-Gossett, you have 100 grams of barley seeds and they yield 10 kilograms of barley. Maybe you make a 95% confidence interval that the population mean for this barley that you sampled is somewhere between, let's say, 8 and 10 kilos, that you use the t distribution, you use your standard deviation, you figure out this is the confidence interval for your population for that barley. You could also, for your other barley, maybe you find that your 100 grams yielded 20 kilograms for your other sample, your other variety of barley. You might build your confidence interval again using this distribution, and you would say that the population mean for this population of barley is somewhere between 19 and 21 kilograms. Now you would say that those population means don't include each other in those confidence intervals. You can be confident that those means are not the same, that those populations are not the same. And this is exactly what a t-test is doing. If barley A and barley B came from the same population, that would be our null hypothesis. There's no difference between barley A and barley B. Then we would expect their sample means to be pretty similar. We would expect them to be within a standard deviation or two of each other, depending on how big our sample was. That would be our null hypothesis. But if we observed a big difference between these two means, between the yield for barley A and barley B, that was many standard deviations bigger, that one mean was many standard deviations bigger than the other, then we could say that it was highly unlikely that it was less than a 0.05 probability of observing that difference. That is where our t-test comes from. That's where our p-value would come out of our t-test. That would mean we can reject our null hypothesis that these barleys come from the same population, and instead we would support a different hypothesis that barley A and barley B have different yields. And because we had means for each one, we could probably say barley B yields more barley than barley A. That's just the Sealy-Gossett Guinness barley example. But let's also make sure we talk about it in terms of our headphone example. We'll get over to the headphones experiment. So the t-test is used when we want to compare means between two groups. This is your big indication, again, that you're using a t-test. You're comparing means between two groups. When we run our t-test, we're asking if our sample means, if the sample from one condition and the sample from the other condition come from the same population. And when I say population, I mean that each observation is normally distributed around one mean. Our t-test might reveal samples that are not likely to be normally distributed around one mean. You might expect that it's actually normally distributed around two different means, that there's kind of a mean for your headphone group and a mean for your control group, and they come from different means. That would be our first indication that we have different populations overall. Simplest explanation for this kind of bivariate distribution, this distribution with two means, is that you have two different populations. Why might we have different populations? It's not that the people who are wearing headphones are different people altogether than people who are not wearing headphones. It's not that they come from different like demographic populations in that way, but it's different statistical populations. It's that our independent variable is having some influence on the dependent variable. For the cycling example, it's not that the people themselves are different, but it's that wearing headphones causes different cycling scores, that it's not just the individual that's causing their own score, it's some combination of individual characteristics and the characteristic that you're wearing headphones or not wearing headphones. And because the only difference between the participants in one condition and the other is that independent variable, because we're holding everything else constant, it lets us conclude that the difference between the populations is caused by our independent variable. This is how we make our causal conclusions. So when I say that, so that's how we make our causal conclusion that the independent variable is causing a change in our dependent variable when we observe very different means between the two conditions. When I say very different means, how different are we talking about? That depends on your sample size, but it's in terms of standard deviations. It's how many standard deviations away from one mean was the other mean. And the bigger your sample size is, the closer, the smaller number of standard deviations away you need to be to find a significant difference. If you have really, really small samples, then you might expect some pretty different means just by chance alone. But as your samples get bigger and bigger, it becomes less and less likely that you're observing really different means just due to chance. Instead, when you observe really different means and you have a really high, and you have a relatively high sample size, then you're probably observing two different populations. Someone said, does that also eliminate populations with different variants around the same mean? Spread is different. So yes, one of our assumptions, yeah, that's actually a really good question. I at first didn't catch what you meant, someone who DM'd me. But yeah, if each of our variables have different variants, then we can't really compare them very well because I'll get to it, that's one of our assumptions of a t-test, that if our two different conditions have different variants, then we might expect to find pretty different means between them just due to their own difference in variance. So one of our assumptions will be that they have similar variants. So that's a really good question. That's really getting to the heart of a t-test. So let's look at a histogram, by the way, for our headphones cycling example. This might be one histogram of the experiment. So I generated some fake data. I made overlapping histograms. In green, this is the headphones condition. It looks normal-ish, and it looks like it's kind of centered around 4 or 5. And then in orange is the control condition. It looks normal-ish, but maybe pretty peaky. And it's more centered around 5 or 6. It looks like we have two different means when we look at the two different conditions on their own. This would kind of visually be our first indication. My voice cracked there, so I wanted to say it again. This would be our first indication that our samples come from different populations. If our samples came from the same population, then we would expect a lot more overlap. The groups might not have exactly the same distribution. There might be this kind of some overlap and some, one group having some on one side, some on the other, but we wouldn't expect it to be so clear that one group was higher and one group was lower just by chance. So to summarize our rationale for the t-test, we use this test to assess whether the means of two samples are likely to have come from the same population. We are testing the null hypothesis that there is no significant difference between the means of the samples that we've collected. Large differences between the sample means from a single population are rare, but how large is a large difference and how rare is rare? Well, that's what the t-distribution helps us answer. Depending on the standard deviation of the groups we observe and of the sample size of those groups, we can determine just how unlikely it was to observe two different samples with two different means that come from the same population. And that's how we get a p-value for our observation. That's how we test against our null hypothesis that the samples come from the same population. If the p-value is very, very small, it was very unlikely that we observed two samples that came from the same population and that our difference in means was just due to chance. In that case, we can reject the null hypothesis. We can conclude that our samples came from different populations. And because our experiment made sure that the only thing that was different between our samples was the independent variable, that lets us conclude that the difference between means in our groups was caused by the difference in conditions for the independent variable. That is to say, with this research example, a p-value of less than 0.05 for our t-test would let us reject our null hypothesis and support our research hypothesis that wearing headphones while cycling causes a significant change in cycling ability. So this is, we'll get to generating this, but this is a bar plot with error bars. This is a great way to visualize a difference between two means. The error bars represent one standard error. You can kind of go back to our lecture on variance to remember what that means, but I'll also show you in the practical and the coding portion of today's class. Now, depending on our experimental design, there's two different types of t-tests we might use. If we're using a between subject study, like what we discussed for this headphones cycling experiment, where each participant only experiences one condition or the other, then we would use an independent means t-test. This version of the t-test compares the scores of one group, the cycling scores or whatever your observations are. It compares the means of those scores to the means of the scores of the other group. And it assumes that there is no relationship between any given participant's score with any other participant's score. So, participant 1's score did not impact participant 10's score. You might hear my cat meowing loudly in the background. I hope she's making yet another guest appearance today. If, on the other hand, if we don't have a between subjects design, if we have a within subjects design where every participant experiences both conditions, then instead we need a dependent means t-test, aka a paired samples t-test. These are the same exact thing, just different names for the same thing. But a paired samples t-test assumes that participants' scores in one condition are related to their own scores in the other condition, because it's the same person producing those scores. Instead of comparing the means of scores in one condition to the means of the scores in the other, you're just getting the means of the differences between scores for each participant. So you're just taking for each participant, you're getting a difference between their scores, subtract one score from the other, that's their difference. Get the next participant's difference, so on and so forth. And you're comparing that mean of differences to 0. The null hypothesis is that there should be no difference between conditions, that each participant's score will not differ between conditions in any significant way. Your research hypothesis would be that everyone's score differs kind of in the same way, in the same direction, that headphones make everyone worse at cycling. And that's what a dependent means or paired samples t-test is assessing. So when we run a t-test in R, this is what the output looks like. I've highlighted the 3 kind of important things we need to look at. We just run, it's a really simple command. You just run t.test, and then you specify one condition, the other condition, and whether this is a paired t-test or not. So either paired equals false or paired equals true. We said we're doing a between subject study, so it's an independent means t-test. So we want paired equals false. We run this command and we get a handy little output with the 3 main numbers we are interested in. We get the t statistic, so that's the ratio of the differences in the means. That you don't necessarily need to know or interpret the t statistic, but you do need to report it when you report a t-test. You get the degrees of freedom, which we'll talk about more in a moment. This is just the number of participants minus the number of groups in this case. So I actually had 32 participants in 2 groups, so we would have expected 30 degrees of freedom. R also bumps that down if your assumptions are not perfectly met. So just like with the regression tests, where your degrees of freedom might be a little bit different than you expect because R is penalizing you, it's doing the same thing here. It's giving you a slightly smaller degrees of freedom. It's making you have to use one of those flatter t distributions instead of the really peaky one where it's really unlikely to observe even a small difference. It's making you use a flatter t distribution. That way, it's still somewhat likely you observe bigger differences. That way, it's less likely that you get a significant p-value. It's punishing you for not fully meeting your assumptions of the test. You don't have to worry about the math that goes into how that penalty works. Just know that R is making a more conservative guess for you. That way you can be more confident that your p-value is significant, even if your assumptions aren't perfectly met. And underneath those numbers that we're interested in, R will also give you a confidence interval for the difference between the population means. So the true difference between the headphone condition and the cycling condition was somewhere between 1.16 points and 3.07 points. And it will also tell you what the sample means were. So this is the actual mean that we observed for control, and this is the actual mean we observed for headphones. So this is a really handy output, and it makes it really easy to report your t-test. When you report a t-test in words, you just need those three parts that I highlighted: the t statistic, the degrees of freedom, and the p-value. So we would report t, and then in parentheses, degrees of freedom equals our t statistic, and then comma, our p-value. Putting it into words, we could say something like mean cycling scores for the control condition, mean equals 5.75, was significantly greater than the mean cycling score for the headphones condition, mean equals 3.64. T of 24.56, that's our degrees of freedom, equals 4.57, that's our t statistic, and p is less than 0.001. We might also add something like, this supports hypothesis 1, that there is a significant difference between cycling conditions on cycling score. And then to visualize that difference, we might include a bar chart with error bars, like I showed you a couple slides ago, and like we will do in the practical today. So that's how you report a t-test, but we also want to go over two things. First, what the heck is a degree of freedom? I keep using that word and I haven't explained it all year. And two, what are our assumptions for using a t-test? So let's do the degrees of freedom question first. Let's finally have this conversation. When I say degrees of freedom, what the heck am I referring to? Degrees of freedom are how many observations are free to vary when I'm calculating a statistic. So again, what does that mean? Let's take an example of what that looks like. Let's say we have 3 siblings and their mean age is 10. How old are our siblings? Well, there's a lot of options here. They could be 10, they could all be 10 years old. They could be 8, 10, and 12. They could be 5, 10, and 15. We have degrees of freedom. We have numbers that can freely vary. How many degrees of freedom do we have? How many of these numbers can freely vary? Let's find out. We know that we have at least one, because when we start out, we can pick anything for this first number. There's no kind of limitation on what our first number is. So let's pick something. Let's pick 12. So we know one of the siblings is 12, and we know that their mean age is 10. Do we have more degrees of freedom left? Do we have more than one degree of freedom? Can we pick anything we want for this second number? Well, yes, there's still no limitation. The siblings could be 8, 10, and 12. They could be 5, 12, and 13. Does that math work? Yes, they could be 5, 12, and 13. They could be 12, 17, and 1. So we still have at least one degree of freedom, more than just one. So we have at least 2 degrees of freedom. So let's pick a number. Let's pick 12 again. So sibling 1 is 12, sibling 2 is 12. Do we have another degree of freedom? Is this third number free to vary? No, it's not. We actually only have one possible number that we can pick for this third sibling. It's 6. That third sibling must be 6 years old for everything else to be true, for these 2 to be 12 and for their mean age to be 10. So we know that our third sibling is 6 years old. That was not free to vary. We had a degree of freedom for our first number. We had a degree of freedom for our second number, but we did not have a degree of freedom for our third number. So for these 3 siblings, we had 2 degrees of freedom. That's kind of example number 1. Example number 2, let's say we have 3 siblings who have a mean age of 10 and the standard deviation of their ages is 2. How many degrees of freedom do we have now? Now, this is a weird kind of contrived example. I'll let you puzzle over what situation you would know people's mean and standard deviation of ages, but not their actual ages. But we'll just pretend that this is a real example. So we have 2 knowns. We have their mean and their standard deviation, and we have to figure out what their ages are. Do we have at least 1 degree of freedom? Could we put anything we want in here? Well, yeah, we do have at least 1 degree of freedom. We could pick at least some number here, and then that might leave us more constrained for our other numbers. But let's pick something. We have at least 1 sibling, we'll say, is 12. That was free to vary. Now, do we have any more degrees of freedom? I'll let you puzzle over whether or not there were other possibilities on your own, but It turns out, no, actually, we don't have any more degrees of freedom after that. We only had the 1 degree of freedom, that if one sibling is 12 and we know the mean is 10 and the standard deviation is 2, the only ages that can fulfill the rest of this mystery are 10 and 8. That once we've picked one number, these two are fixed. They're not free to vary. We could have picked 8 or we could have picked 10 here, but that would have locked us into the other two numbers for the other ones. We would have known as soon as you pick one, the other two are not free to vary. This is the idea of degrees of freedom. And we said hypothetically, the first two siblings could most likely be twins since they're the same number. Yes. So for the first example, our 12 and 12-year-olds were probably twins, and our third sibling was 6. In that case, it's fine that we had two numbers that were the same. This is just like in our when we have a sample of, let's say, headphone wearers' cycling scores, that if my first participant had a cycling score of 7, there's nothing that rules out the next participant also having a score of 7. There's no assumption of variance when we calculate the mean for our condition in that way. But when we count up our total degrees of freedom, we're going to end up with 1 minus the number of parameters we're using. So if we know the mean and we know the standard deviation, we had to calculate them somehow. So if we know our mean, if we know just our mean, if we know just one parameter, then we have our sample size minus 1 degrees of freedom. If we have 2 known parameters, this time a mean and a standard deviation, and we have sample size minus 2 degrees of freedom. And you can kind of, you work it out by going backwards like this. You start with your, whatever your known parameter is. So you've calculated your mean, then you work backwards to see how many were free to vary, just like I'm doing with these silly examples. So for example 1, we had 1 parameter. So we had n minus 1 degrees of freedom. We had three siblings, 1 parameter, so 2 degrees of freedom. This time we had 2 parameters, 3 siblings minus 2 parameters. We had 1 degree of freedom. Degrees of freedom denotes how many positions are fixed, and SD here just denotes standard deviation. So I told us that in my example, standard deviation was 2. Degrees of freedom denotes how many positions are free to vary. So degrees of freedom is your sample size minus your number of parameters. But that's generally the right formulation, that these are the number of values that were free to vary, that were not fixed, that you could have substituted any value into. SD here was just a different parameter I was using. I could have done variance, I could have done median, whatever other statistical calculation. I just picked standard deviation randomly there. Let's do one more quick example. This time it's going to have a little bit of an interactive quiz component, but let's say we have 3 siblings with a mean age of 10. They have 3 pet cats, and the pet cats have a mean age of 6. How old is each sibling and how old is each cat? How many degrees of freedom do we have? You can throw guesses into the chat if you think you know, but we can work through it one step at a time. So how many degrees of freedom do we have for 3 siblings, 3 cats, 2 means? We can start by picking out an age and a sibling for each cat. So an age for each sibling and an age for each cat. We can burn 2 degrees of freedom right away. So we'll pick one here, we'll pick one there. And do we still have some degrees of freedom? Yeah, we still could pick any age we want for the second child and for the second cat. So we've found that we have 2 degrees of freedom. We still have more remaining. Let's pick another sibling and another cat. We'll pick 12 and 10 for the siblings. So we've used 2 degrees of freedom here. We've used 2 more degrees of freedom here. So we now have 4, we've used 4 degrees of freedom. And now, yeah, I've gotten DMs now. People are saying 4 degrees of freedom is correct. We don't have any more degrees of freedom. We don't have any more, we can't freely choose this last sibling, and we can't freely choose this last cat. We had 4 degrees of freedom because you can think of this as either 2 groups with sample size of 3. So we had a total population of 6 minus 2 groups. So we had 4 degrees of freedom. Or you can say we had a total population of 6 and 2 parameters. We had mean of siblings and mean of cats. So sample size minus number of parameters is your degrees of freedom. So yeah, that's your solution. If you were wondering about the siblings and cats' ages in my example, you could have picked other numbers, but Suffice it to say, once you've picked 2 siblings, the third sibling is not free to vary. Once you've picked 2 cats, the third cat is not free to vary. Because in a general sense, your number of degrees of freedom is your n, your sample size, minus your k, your number of parameters. So for t-tests in particular, let's talk about how you can calculate degrees of freedom, or how R is going to do it for you. For an independent means t-test, you have n participants, and that means you have n observations that each participant experiences only one condition or the other. And you're taking the mean of each condition. So you're taking 2 means in an independent means t-test. So your number of degrees of freedom is n minus 2 when you have a between subject study, when you have an independent t-test. When you have a dependent means t-test, a paired samples t-test, you have n participants, but you have 2 times n number of observations. That is to say, each participant gives you an observation in both conditions. But remember I said you're not taking the mean of both conditions. You're actually just getting a difference for each participant and taking the mean of the differences. You're only calculating one mean, so you only have one parameter. So your degrees of freedom for a dependent or a paired samples t-test is n minus 1. That means there's kind of a plus and a minus to doing a between subjects or a within subjects study for a t-test. For between subjects experiment, if you wanted 40 observations for each condition, you would need 80 participants, and you would be left with 78 degrees of freedom. If you did a within subjects experiment and you wanted 40 observations for each condition, you would only need 40 participants, but you would only be left with 39 degrees of freedom on a paired samples t-test. So it would be easier to recruit for the within subjects experiment. It's a lot easier to get 40 people to agree to do your study than to get 80 people to do your study, but you would have reduced statistical power. You would have to use one of those flatter t-distributions that even if you found a somewhat more extreme difference between means, you would be less confident that that difference was due to a difference between populations. You might just get an insignificant p-value for the same difference because you're using this flatter t-distribution, because you had fewer degrees of freedom. And you can, again, look at the distribution that for a very high sample size, you get these really kind of tucked in tails that it's very unlikely to observe a big difference if you have a very high sample size. But as your sample sizes are smaller, this is like an infinite sample size or a normal distribution, basically. Sorry, a normal t-distribution. Nope, I don't know. Never mind. Pretend I didn't say anything there. This is for an infinite sample size. This is for a sample size of 5. This is a sample size of 2. That's a sample size of 1, or rather, these are degrees of freedom. So 1 degree of freedom, 2 degrees of freedom, 5 degrees of freedom. As you have more degrees of freedom, it becomes less and less likely to observe extreme differences. So the bigger your sample size is, the more confidently you can detect even very small differences and find them to be significant differences. That's the benefit of a large sample size, that you have more statistical power to conclude that the effect that you observed is significant. So quickly, let's also talk about the assumptions of our t-test. Now that we've talked a bit about degrees of freedom, there's a few things we need to check before we can run a t-test. First of all, you need to make sure that your dependent variable, your, in this case, cycling score for us, is either interval or ratio data. So it should be a number rather than like a category or a rank or a label. Next, your data should be normally distributed. So we will also talk about how to measure normal distributions without just doing the eyeball test, but both for an independent means t-test, that means both conditions should be normally distributed on their own. It doesn't matter, the data altogether doesn't have to be normally distributed, but between conditions, each condition should be normally distributed. Again, if you looked at the histograms I showed for our control and our headphones condition, together they weren't super normally distributed, but when we looked at each individually, we concluded that they were. If you're doing instead a within subjects study, if you're doing a paired samples t-test, then the thing that you need to test if it's normally distributed isn't each condition, but it's actually the differences between conditions. Again, when we do a paired samples t-test, the thing that we're measuring, the thing that we're taking a mean of, the thing that needs to be normally distributed is the difference between conditions for each participant. In the next slide, I'll show you how to use the Shapiro-Wilk test. That's how we can conclude decisively whether or not we had a normal distribution, rather than just having to look at it and say yeah, I guess that looks normal. so those are our only two assumptions if we're doing a paired samples, a dependent means t-test. If we're doing an independent means t-test, we have two other assumptions. One is really simple. It's that the observations are independent, that they come from other people, they come from different people. That goes without saying. If you're doing a between subject study, you can't have any participant that is in both conditions. The other important assumption that someone brought up in chat earlier is that the two conditions have similar variance, that the variance of one condition is equal or pretty close to equal to the variance of the other condition. This is the assumption of homogeneity of variance, and we use the Levine's test to test that, and I'll get to that in 2 slides. So we have 2 assumptions tests we're going to be going through, and we're going to start using from here on out. The Shapiro-Wilks test, test normality, and the Levine's test to test homogeneity of variance between conditions. Somebody asked, can I explain the advantage of a higher degrees of freedom? I'll quickly do this. I realize I'm getting a little tight on time, but notice that for this is degrees of freedom. As degrees of freedom increases, the peak of this probability distribution increases, and the tails get lower. So let's pretend in general, we have an independent means t-test. We have 2 conditions, and we observed that the difference between those means is 3 standard deviations. So it's right here. If we had a really small sample size, like 2 degrees of freedom, that difference of 3 standard deviations would be right around 0.05, but we might not say that that's a significant difference. We might be like, we're just not sure if that difference was due to chance. We had a p-value of 0.06, so we can't actually conclude that this was a significantly different, that these 2 means were significantly different. If, however, we had a really high number of degrees of freedom, if we had a really big sample size, notice how much flatter the distribution is here. Now at 3 standard deviations, the p-value is here. It's like way down here. It's like 0.001 or something. In that case, we would conclude that our difference was significant. So even though the difference we're observing is the exact same number, it's the exact same number of standard deviations, having a larger sample size makes us more confident that that difference is due to an actual difference in the populations, that it's not just due to chance. So having a higher sample size, having more degrees of freedom, means we're less likely to miss a significant difference. We're less likely to have a false negative, to say that there was no significant difference when a difference actually existed. That's the big advantage of big sample sizes, big degrees of freedom. So quickly, before we get to the practical and before we take our break, we have 2 assumptions tests. The first is the Shapiro-Wilk test. This is a parametric test that compares the shape of your distribution against the shape of a normal distribution. The null hypothesis for this test is that the 2 shapes, the 2 distributions, are not different. In other words, the null hypothesis is that your distribution is normal. So this is the rare time where the null hypothesis is the thing that we really want to be true. We want your distribution to be normal. So that means we want a p-value, and we expect a p-value to be bigger than 0.05. When we see this p-value of 0.686 or whatever, that means that the Shapiro-Wilk test is saying, yeah, it looks like your distribution is normal. We are really happy to see a high p-value in this case. We're not rejecting the null hypothesis. We're accepting this null hypothesis that our distribution was normal. That's great. That's something that's true of both of our assumptions tests. A high p-value is a good thing. It's the thing that we're looking for. And that's because the null hypothesis is that your distribution is normal with the Shapiro-Wilk test. And this is super easy to run in R. We'll run it today, but it's just Shapiro.test, and then the name of the object in your environment that you want to test if it's normal. So in this case, I have control is my control condition cycling scores. And it's saying, yep, we're not rejecting that null hypothesis. Your control condition is normally distributed. Our other assumptions test is the Levine's test, and it's really similar. This test is to test the assumption of homogeneity of variance, the idea that the variance in one condition was equal to the variance in the other condition. Just like the Shapiro-Wilks test, the null hypothesis is the thing that we want to be true. So in this case, the null hypothesis is that the variance between the 2 conditions is equal. Just like the Shapiro-Wilks test, that means we're hoping for a p-value greater than 0.05. We're hoping for, expecting a big p-value because we do not want to reject the null hypothesis. The output for this test looks pretty similar to a regression model because it actually is running a type of regression model. It's comparing two models. It's comparing a model of the variance of one of your groups and the model of the variance of the other group. And all we need to report, all we need to care about is this p-value. And again, here we found this p-value it's really close, but it is bigger than 0.05. It's 0.075. So in this case, we would say we are not rejecting the null hypothesis. We would say that our variance is homogeneous, that we met the assumption of homogeneity of variance. The two conditions had similar variance. We could report this in words with like a single sentence in our data cleaning section. We could say something like, data was normally distributed, and in parentheses, the Shapiro-Wilk test, p is greater than 0.05, and there was homogeneity of variance. And in parentheses, Levine's test, p is greater than 0.05. That's all you would need to say about that. You don't need to show me your output or your exact p-value or f-value or anything. Just tell me that it was greater than 0.05 and that you checked that those assumptions were met. A quick line like that is plenty. So if both of those assumptions are met, then you don't need to report anything but the p-value. Yeah, you can just, as I said, have a line like data was normally distributed and there was homogeneity of variance. Just a line like that in your data cleaning section is all you need to let your reader know that those assumptions were met, that you did check your assumptions of your t-test. You know, just like you're not showing your reader histograms or box plots or R code outputs, that those are tools for you as the data analyst. You also don't need to show them all of the output of your Levine test or your Shapiro-Wilkes test. You can just give them this information and that will help them understand your quantitative analysis. So that's it. That's the t-test lecture. Your reading for this week is chapter 9 that covers both the independent and dependent means t-test. I saw some comments, by the way, in the course feedback that people mentioned the book is helpful upon rereading or rewatching. So I saw someone say they like to come into the lecture cold, not knowing anything about this stuff. Then they read the book chapter and it helps somewhat. Then they rewatch the video and then it's really clicking. And then when they come back to the book to study or to write an assessment later, then they're like, okay, it's all good now. So hopefully that like interplay going back and forth helps you. If not, if you're trying, you're going back and forth and certain parts still aren't clicking, get in contact with us. Email us, book an office hour. We are happy to either recommend more resources or to talk things out. We are big nerds and we love talking about statistics. And if you didn't complete the feedback form, but you still want to, I will keep checking it. We only have a couple more meetings left in the year, but the feedback still helps me grow as a teacher. It helps me make this class a little better for the remaining time we have left, and it helps me make it better for next year. So if you still want to let your voice be heard, please let it be heard. Anyway, it is 2:59 by my clock. So I want to give you your full 10-minute break and we will convene at 3:09. I'll see you back in 10 minutes. Feel free to keep questions coming in the chat. I'll try to answer them either in chat or out loud as we start the practical. And yeah, see you in 10 minutes to do some R coding. First assignment results and feedback should come back to you. I just got the DM, but first assessment results should be back to you 2 weeks from today. So before our meeting in 2 weeks, which is our review meeting before the multiple choice test. We are trying our hardest. This is the biggest QDA has ever been by a huge margin, but we think we're going to get them back in time for that class. So they'll definitely be back well in advance of your second assignment being due. Anyway, enjoy your break and I'll see you in 10 minutes. All right, hello, welcome back. I did get one question in chat that I did want to address, which is someone asked, what does the T statistic signify? What does that T value tell us? That's a good question. I had it in my slide notes, but I was like, I'm going to skip saying this because it's a little bit mathy, but I can share that now. I don't have the formula in a slide, but it's in the book. But the t statistic tells us the ratio of the mean, or of the difference between the means, the ratio of that number, that difference between means, as compared to the ratio between the standard errors of your two groups. So the person also asked, does the t statistic affect the p-value? And yes, it does. So that p distribution that we saw is the same distribution so that's the t distribution for just comparing a single number to a mean of 0. But if we're comparing two means to each other, that same distribution describes our t statistic. So a t statistic of 0, where there's no difference between the means, or the ratio between the means is very small compared to the ratio between the standard errors, would be kind of clustered in on the center. That's where the big peak of that graph is. And then as our t statistics get larger, they're more out towards the tails. So depending on what our sample size is, depending on what our degrees of freedom are, the bigger the t distribution, the more likely it is to find a significant p-value, to find a very small p-value for that t statistic. So the t statistic follows that same exact t distribution that depends on your degrees of freedom. And it just talks about the ratio of the difference between means in your conditions, the ratio to the difference between the standard errors of the conditions. So that's what the t statistic means. And it's, it does affect your p-value. It's that same distribution. Find your p-value based on your t statistic. Oh no, I have an old plot up. I was grading papers right before class, and that is someone's plot from their assessment. I will hide that now. Remove the current plot. Plot thickens. I will clear all plots in my library, and I will clear my global environment so we can do this from the top. We are going to try to do the same t-test that we described in the lecture today. So I keep leaving it as 2021. I'm giving away that I'm just using my code that I wrote last year. But as always, we're going to set our working directory. You may or may not have a separate folder by week. I don't. So I'm going to set my working directory to QDA 2022. Clear my environment also, clear my console. So I'll set my working directory. I'm going to read in the new data. So hopefully you did download the cycle data CSV and you put it in your QDA working directory. So when you run that line, you will read in your new data into your environment, and we'll check out the head and the tail of that data. And this time, because we have an experiment with two different conditions, it's actually important that we leave this subject number column in, because now we actually do need that subject column to know whether this was a between or a within subject study. So it looks like we have 32 rows of data and there are 32 different subject numbers. So that means we had a between subject study. It means that every different row of data came from a different subject. Every observation was independent. So this week we will leave that in. We'll also see that we have a categorical variable called condition, which is either control or H phones. And we have a numerical column, a numerical variable called score. And that again was score on the cycling, their cycling score as assessed by like an expert rating them on a scale of 0 to 8, or by a team of 3 experts, because we have like these decimal scores. So these are like average scores between the 3 experts' ratings. So when we have a condition variable like this, when we have a categorical variable, one thing that we should always do is to let R know that this value, that this variable is important, that each different level of this variable is a different level of our independent variable. These aren't just arbitrary names, that these are actually levels of some independent variable. So to do that, we can tell R that it is a factor. We can tell R, we use the factor command. So we're saying treat cycle $condition, treat this column as a factor, and then just save over whatever you have it as now. So just don't think of it as just words. So right now it probably considers this just a like a nominal variable, like it's just random names that don't mean anything. We're telling R, no, we want you to treat this as a factor, that these are actual levels of an independent variable. So when we ask R, what are the levels of our independent variable? What are the levels of condition? it tells us that this condition has two levels, has two conditions. We have control and we have H phones. So that's just like good like practice, good housekeeping for later on. It won't actually affect our code today if we didn't do that factorizing step. But as you get into either more advanced comparisons between means or in categorical regression models, then you would want to make sure that you always use that factor command just to make sure you're letting R know when you have a categorical value variable, because it won't know if it's actually categories or if it's just like random names or something. So we did that, we factorized condition. Now we want to put each of our two conditions into different subsets. We want to make them each their own item in the environment because we want to do statistical tests on both of them. We want to like get the mean for just one condition, get the mean for just the other. We want a histogram of one, a histogram of the other, all that. So we're actually going to put them into the environment separately. And there's two ways we can do this. I chose, so we're going to use the subset command. The subset command says make a new data frame that only includes certain things. So make a new data frame that only includes cycle $score. So it only includes this column. And it only does that for rows of cycle where condition equals control. So we could have left this out. We could have said, give me a subset with like all of the columns where condition equals control. But I actually don't care about all of the columns right now. I only, because for everyone in control, their condition will be the same. And now that I know it's between subjects, I don't really care about their subject number anymore. So just give me their scores if their condition was control. And now I have, instead of a data frame where it has multiple columns, when you just have one column, this is called a vector in R. So we have a vector is just a list of numbers. So we have this list of scores for people in the control condition. We have 4.1, 5.29, and so on. We have 16 numbers, a list of 16 numbers of cycling scores for the control condition. And we can do the exact same for the headphones condition. So we have two objects in our local environment that are in our global environment that are just vectors, that are just lists of the cycling scores for each condition. And if we just call the name of that variable, if we just say headphones, it'll just read out the list to us. It'll tell us every item in that list. So now we can run our descriptive statistics for the cycling scores overall and for each condition. But as you guys keep bugging me about, like, is there a better way to do descriptive statistics than having to write it all out every time and copy and paste new things in? There is. Early on, someone asked me, like, isn't there a simple command we could run? There is, but kinda. There's like a bunch of like okay commands that have like a few of these descriptive statistics. But in my estimation, none of them have like all of the ones that I want. And this was Ben, the module coordinator's opinion too. So he wrote a little R program, a little code called summarystats.r. And this is just an R script, just like what we are writing in class, where he defines one function. He just makes up a new function called summary.stats. If you're interested in writing your own functions, you can read in there. You can check out how functions work, but you don't need to learn how to do that. We're writing this function for you, and you can use it however you want. So now if I run summary.stats of control, it gives me all that information. It gives me min, max, mean, median, variance, standard deviation, interquartile range, and n, so sample size. And that makes my life a lot easier. So for your next assignment, if you want to reuse this summary stats command, feel free. You just need to run this source summarystats.r, and that will let you use this summary.stats command. You can run summary stats in one line of code for your entire object. So feel free to do that if you want to, but you don't have to. If you don't want to, you can run these by hand just as easily. It's all the same. So yeah, like I said, just make sure that that summarystats.r file is in your working directory, and then just run that source command with its name in quotes. That way you can use the summary stats command if you ever want to in the future. So that is our descriptive statistics. Now let's check our assumptions and check that our data is clean and, you know, all that stuff. Let's do our box plot of cycling scores overall. And this is, I'm just checking for impossible values right now for something that's outside of our possible range. And it looks like our range, as I said in the lecture, was from 0 to 8. So we're all good there. No one in either condition was outside of that range. Now we want to look at box plots for each condition. It's just to kind of start getting a visual approximation if we think there's going to be a difference between means. You don't necessarily have to do this, but it's just nice practice to get to know your data a little better. So you can run two different box plots, one for control and one for H phones. Or this is a little bit of a fancier method that I'm showing off this week. You can say box plot of cycling $score, so box plot of the numerical value, and then that little tilde that we used in the regression commands. Box plot of this variable, and whenever I read this tilde, I read it as the word by. So give me box plot of cycling scores by cycling condition. And then I also have some extra stuff in there, a title, a Y limit, so my range, my X label, my Y label. So when I run that, I get two different box plots, one for the control condition and one for the H phones condition. And now as like a data analyst, this is super helpful for me because I can look at them and I can say, oh yeah, look at this median is like so much higher than that median. I'm really thinking that these are going to be significantly different. My only question is like, is my sample size going to be big enough? My other question is my variance going to be homogeneous? Is it going to be the case that my Levene's test gives me a p-value greater than 0.05? Because it looks like there's a really small distribution of scores in the control condition and a bigger distribution of scores in the headphones condition. While I'm here, I'm also noticing that there's no outliers in either condition, so that's good. But I'm starting to worry about one assumption, but I'm checking other assumptions off my list. So that's why I might run this box plot with them right next to each other. Now, I also showed in the lecture stacked histograms. So I might want to make histograms where one is a histogram for one condition is right on top of the other condition. So again, I can just visualize them both at the same time. I don't necessarily need to do that. I could just run two different histograms, one for control and one for headphones, and then just kind of go back and forth looking at them. But just like visualizing these right next to each other lets me start to visualize that there is a difference between my conditions. That's the same reason I might want to visualize my histograms together, visualize both conditions in the same histogram. So to do that, I know that I'm going to draw one histogram on top of the other. So I'm going to include all my normal stuff for my histogram. So I'm going to make a histogram of control. I'm telling it my X limit is from 0 to 8. I'm telling it my breaks are from 0 to 8, counting by 1. And I have one new parameter this time, and that's color. And now you can specify color with quotes and a word. So I could say color equals red. But when you do that, when you specify by word, it assumes that you want a fully opaque color. That is to say, you want a color with no transparency. And that wouldn't be great if we're stacking bars on top of each other. We want them to be a little bit see-through so we can kind of see one through the other, that when you draw the second histogram, it doesn't just draw right on top of the first one. If it did that, you wouldn't be able to see the first one that you run. So it would kind of defeat the purpose of running both together on the same plot. So I want a histogram with a little bit of transparency. So I have another command for generating colors called RGB. And this is a really simple command. It just takes 4 numbers. The first number is your proportion of how much red you want. So I want 100% red. I want proportion, next number is G, green, your proportion of green. I want 50% green. And I want 0 blue. And I want my fourth number. This is RGB calls your fourth parameter alpha. I call it transparency. So I want this to be 1/3 transparent. I want it to be a little bit see-through. I want to still see my color, but I want to be able to see something else when I draw on top of it. So I want a somewhat transparent orange color. It's mostly red with a little bit of green in there. And you can see where this is going. I pick orange and green for 2 reasons, actually. I learned a couple years ago teaching this class. Someone in the feedback forum actually told me, hey, you use red and blue as your colors for plots most of the time. And that's grand, but I am red-blue color insensitive. It's sometimes really hard for me to tell the difference between the 2 colors that you're showing. And I didn't realize before that student alerted me to that that's a pretty common color insensitivity. So I did some research about what colors are good for lots of different people's visions. And I found that a light orange and a light green contrast each other really well. And it's pretty good across a lot of different color blindnesses and color insensitivities. And it has the secondary benefit of being the flag of Ireland. So now every time I generate plots with 2 colors or 3 colors, I go for that white, red, and white, orange, and green. Go for the tricolor. It's a really handy little like a really like nice coincidence that not only is it good for color blindness, but it's also good for just like branding my work when I publish papers. It's like, he's the guy with the Irish bar graphs. That must be one of Justin's papers. So anyway, when I want to draw a second histogram on top of this one, I can leave out most of my parameters. So I want a histogram of headphones right on top of this histogram of the control condition. But I don't need to specify an X label anymore, or a main title, or my limits, or my breaks, because it's going to use all the same stuff that's already there. All I need to tell it for the second histogram is what color I want. So this time I want one that's 100% green, no red, no blue, and again, 1/3 transparency. And then I add one more argument, one more little parameter to my histogram command, and that's just add equals true. That just means I want this added on top of the last graph that I generated. So if I ran this one first, it would give me some error message. It would tell me add to what? You don't have a plot to add to. But when I have another histogram here, then when it says add equals true, it checks if it can add to, like if these plots are compatible. They're both histograms, they have the same limits and breaks and all, so it's fine with adding that. I run the command and I get my Irish flag of bar graphs, or of histograms rather. Now I have both variables plotted on a single histogram, so I can compare them side by side. So I can say, again, like, it looks like my mean, my median are probably somewhere around here for the headphones condition, somewhere in this bar for the control condition. So it sure looks like I have a difference between my means. I'm also looking and seeing like, yeah, this, especially the headphones condition looks normal. The control condition, it might be normal. Histograms, as we know, can kind of hide our normalcy. It can make things look not normal when it is normal, or vice versa. So maybe I try different breaks and see if it looks any better. There's breaks of 0.5. And again, like, yeah, it looks kind of normal, but this is like where it's becoming more and more obvious. We need something better than visual inspection, better than the eyeball test to tell whether our variables are normally distributed. So we won't rely on this. We have the Shapiro-Wilks test now, but it's still nice for us to visualize this difference and to just check for abnormalities with a histogram and with these overlapping histograms. I also might want to include, in a case like this, where I have different colors signifying different things, I can add a legend to any figure, any kind of plot in R with the legend command. So this is just something you might want to do for your own plots. You might decide it's fine not to. So I demonstrated you can just put all that information in the title. That's fine, as long as you use like a big version of the plot like that, where the title is visible. Of course, if you're putting this in an APA report, main titles don't belong in there anyway. That would be part of your caption instead. But I can also add this legend, and all I added to the legend is the first parameter. This is all in the notes, so you can check it out later. The first argument is just where you want the legend. So I said top left, right up in here, because there was some space there. And the second argument is your list of names in your legend. So the list of things that you want to label. So my list is C, again, it's just that command to make a list. So C, control, and headphones. And then my last argument is what colors I want. So fill, so instead of, so I want a filled box, I want fill to be the first color and then the second color. And I'm just copying the same colors from my histogram. So that makes it look nice. I have a nice little legend. I could now use like a much cleaner title because I have all that information in a legend now. Just a nice little way to like compress information, make things look a little nicer. But it's up to you. This is like stylistic stuff. But I figured I would start showing some of these like slightly more advanced methods in R, just in case you want to start going a little further, or in writing your thesis, or in other research that you do outside of this degree. If you want to do slightly more tricky things in R, here's like a little bit of a basis for starting to do that. So anyway, I've looked at my histograms and my box plots. I'm all good on outliers. I'm all good on impossible data, impossible pieces of data. My only questions remaining are whether my conditions are both normally distributed, and I'm especially kind of worried about this control condition. And my secondary worry is whether or not I'm violating the assumption of homogeneity of variance. And that's because it looks like I have a lot of variance for headphones and not a lot of variance for control. In fact, I can go back up and look at my summary stats. It looks like my standard deviation for control is less than 1. My standard deviation for headphones is 1.6. So we shall see if those are close enough to be considered homogeneous variance, or if that assumption is going to be violated. And we can do that with our assumptions tests. So first I will run the Shapiro-Wilks test. I'm going to check for normality for each condition. So first, let's see if our control condition is normally distributed. And the Shapiro-Wilks test gives me a p-value of 0.68. Remember, our null hypothesis for our assumptions test is that our assumption is being met. Our null hypothesis for the Shapiro-Wilks test is that this distribution is normal. So we don't have a p-value of 0.05. We are not rejecting that null hypothesis. We are saying that our distribution was normal. That's a good thing to see that big p-value. We will do the same thing for our headphones condition, and this one is super normal. This is almost a p-value of 100%. Yeah, that's great. It looks like both of our distributions are normal, so that assumption is met. We can carry on with a t-test. By the way, quick aside, if we had failed this assumption, or if we had failed the homogeneity of variance assumption, what do we do then? As you're probably catching in the textbook, but maybe you aren't catching yet. If you fail your assumptions for these parametric tests, there are backup tests. There are non-parametric tests. That is to say that they don't rely on the same assumption of normality. They don't rely on the same parametric distributions like that t distribution that I showed you in class today. Instead, they use other methods like ranking to get around those assumptions and to still test what you're testing. So in chapter, I want to say 12, but the chapters are labeled so you can find it yourself. In chapter like 12 or 14 or something of the textbook, there's a chapter called non-parametric tests. We don't cover that in QDA. We only use parametric tests in this module. But if in the future you find that you're not meeting the assumptions of one of your parametric tests and you need to use a non-parametric test, that chapter is super helpful. It kind of has an alternative test for each of the tests we cover in this class. For t-tests, I believe that non-parametric test is the Wilcoxon sign ranked test. It's kind of a kludgy name, but all it is saying that instead of assuming that our variable is normally distributed, we're just going to assume that we're not going to assume it's continuous at all. We're going to assume these are just ranks, and we're going to compare ranks of like our best cycler was in the control condition and our second best cycler was also in the control condition, that kind of thing, and see if our ranks overlap or if our ranks are super different. So that would be the non-parametric alternative if one of our assumptions test was not met. But in this case, our assumption of normality is met. And spoiler, I'm going to give an example where all of our assumptions are met here. So don't worry about that. But if you want to learn more about that, you can check out the non-parametric test chapter of the textbook, or you can email me. My big weakness is if you email me about statistical questions, even if you're not in one of my classes or if you had me as a student years ago, I will eagerly answer. I'm too much of a stats nerd to ignore an email about stats questions. Anyway, to run the Levine's test, this test actually exists in a package in R outside of the base version of R. So we have to download a package. I've already downloaded it, so I'm not going to run this command, but you might need to run this command, install.packages, and then in quotes R. I'm not going to run it because it'll make a bunch of stuff appear on my screen and it'll slow things down because I'll be downloading something. It'll only take about a minute. You'll probably get a bunch of red text, but it's fine as long as this caret appears again and you're able to type in your console, then you're fine. It'll tell you a bunch of stuff messed up, but it's actually completely fine. Once you've installed car, you can run the library car command. And again, I get this like red warning message and some ugly text, but I get my caret back. I'm able to type in my console, so it doesn't matter. I can safely ignore whatever it told me. Now that I've installed and told R that I want to use that library, I want to use car, I can now run my Levine's test. So I can run my test of homogeneity of variance. And remember, I was just saying like this box plot has me really worried that it looks like there's a lot more variance in the headphone condition than the control condition. So we're on the razor's edge. We're a little nervous if our Levine test assumption will be met. And yeah, like I said, it is on the razor's edge. This is the p-value for our Levine's test. It is 0.076. It is just barely above 0.05, but just barely counts. We did meet this assumption, but that's, I'll get to it when we run the t-test command. Because we were so up against violating this assumption, R is probably going to punish us when it runs our t-test. It's probably going to bump down our degrees of freedom by a lot because we barely satisfied our assumptions. That's kind of a nice thing that R does. It makes it a lot less likely for you to conclude that there was a significant difference when there wasn't actually one. So R is like kind of got your back. It's making sure you don't say something crazy by kind of tempering your claims, making it harder for you to find a significant p-value by giving you a smaller number of degrees of freedom. I don't even fully know the math of how it decides how to penalize you. I just kind of accept that it is penalizing me, and I thank R for doing it, so I can confidently make my assertion of whether or not I found a significant difference. But yeah, we've now met all of our assumptions for an independent means t-test. And just to kind of go through it again, our 4 assumptions are that we have a continuous variable, which we do, that is our cycling score, that our each condition is normally distributed. We checked that with the Shapiro-Wilks test. That was all good. We have an assumption that all of our data points are independent. So we check that by making sure that each participant, each row had a different participant number, and that looked all good to go. We might decide to open the whole thing. I only checked the head and the tail. Yeah, sorry, car is like a really big package, so it'll take a minute. That's why I don't run it in class. It shouldn't take more than about like 2 or 3 minutes, depending on your internet connection. But I didn't want to run it and like tank my Zoom call. But don't worry, you never have to run it again. Once you install it once, even after you close R, it'll stay downloaded. You'll only have to run that library command. And as you saw, that took me like a second to run. So you have to endure the pain of installing car now, but you'll never have to do it again at least. If any of you have used ggplot, also I saw maybe 1 or 2 assignments use ggplot. If you've already installed ggplot, then you already have installed car. Maybe I should have told you that ahead of time to save you the trouble. But car, for some of you, will already be there, for others won't be, depending on if you've installed other packages. Anyway, that shouldn't take too long. But now we've met all 4 of our assumptions. Oh yeah, I wanted to say we might want to, I only checked the head and the tail, so I might want to open this and make sure there is a different participant number for every single row. I was confident that there was because I knew there was 32 rows and the last one was participant number 32. But that lets us know that we have independent observations. So that's 3 of our assumptions. Our 4th assumption, homogeneity of variance, we checked with the Levine test, and that was also met. So for our independent means t-test, for our independent t-test, we have met all of our assumptions. We can finally run the test. And this is always like the most anticlimactic thing to me, that we just wrote, you know, including my comments, I wrote 65 lines of code. I guess that also includes like blank spaces. I wrote a bunch of lines of code just to get to this one point to test my hypothesis. And now it's this like tiny little line, nothing to it. I can just run p.test, control, headphones, paired equals false. So one of your conditions, the other of your conditions, paired equals false, and you get this output, the same output that we showed in the lecture. So that's our t statistic. Again, that's the ratio of the difference between means to the difference between standard deviations. You don't necessarily need to know that, but that's what it's comparing on that t distribution. So we have a t statistic of 4. So we're way out, way far from that center of 0. But we only had 24 degrees of freedom. We had 30 degrees of freedom without any penalty, that we had 32 participants and 2 parameters. So our 2 parameters were our mean for our headphones condition and our mean for our control condition. So 32 minus 2 is 30. And then R penalized us a bit because we were so, we had such a close call with this assumption. And also it penalized us a little bit for each of these p-values. It didn't penalize us much for normalcy or normality for headphones, but it did penalize us a little bit for normality for control because that was somewhat normal, but a little sketchy. So that's just an explanation why that number isn't exactly 30. It's just bumped down a little bit. So you make a more conservative answer with your p-value that when you look across on your chart, you're using one of those flatter distributions with higher tails. So when you look across to the x-axis to see what your p-value is, in this case, it is 0.0001. So it's a really, really tiny p-value, even after as conservative as we were being. So if we wanted to report that in words, we could say the mean cycling score for the control condition, m equals 3.75, was significantly higher than the mean cycling score for the headphones condition, mean equals 3.64. And then T of our degrees of freedom, so T of 24.56 equals our T statistic 4.57. And finally, P is less than 0.001. And that is reporting the entire t-test all in one line. That's a nice little concise way to report our t-test. And we also want to visualize our result. So I had that cool bar plot with error bars in the slides. Maybe, your mileage may vary. Maybe you didn't find it cool. I found it. We had that really cool plot in the slides. This is how I make the plot. Well, it's how I'm teaching you to make the plot. You can use the ggplot command, the ggplot package. That's a lot more intense. It involves a lot more coding. But there's a lot of documentation for how to do that in the textbook. I don't get into it in this class, but if you want to learn more about ggplot or like bounce your ggplot ideas off of me, I do ggplot for my own research and R coding and all, so I'm familiar with it at least. But we don't need that fancy command. We don't need that library. We can do this just with the commands R already has built into it. If we're going to make a bar plot, we need the heights of the bars, which are our means. So we need to put our means into one item, one object in the data frame. We don't actually need to put them into one object together. We could just rewrite this list of means every time, this C of mean of control, C is a list, so list of the mean of the control condition and the mean of the headphones condition. We could just rewrite that again and again, but I know I'm going to be using it a few times, so I'm just going to save it as a variable on its own. I'm going to save it to my global environment. So now cycle.mean is now saved into my environment, and it's just a list of the two numbers, the two means. That name, that cycle.mean, isn't magic. You don't need to include the dot. You could have called it cycle means or cycle m or whatever else. You don't need to worry about putting a dot or whatever name you want to use. I just use cycle.mean. Likewise, I know I want to use the standard deviation a couple of times because you calculate your standard error, the size of the error bar, based on the size of your standard deviation and your sample size. So I know I'm going to use those standard deviations. So I also want to just save them as a list and give it a name. So I called it cycle.sd. Again, you can call it anything you want. I also know that I want to use those names, control and headphones. So the same order that I put them in up here, I want to make sure I'm doing the same order every time. It doesn't matter which one you put first or second, just make sure you're using the same order, that all of your means or all of your control condition comes first and then your experimental condition comes second, or vice versa, just as long as it's the same across all of these objects. So I want my names. I want this I want cycle.mean. I want that object to actually be named. I want the first number 5.75 to be called control. And I want the second number 3.63 to be called headphones. So now in the environment, instead of being a list of numbers like cycle SD, it's now a list of named numbers. That's just a little thing I do to make my life a little easier when I'm giving the names for my, when I'm putting names in my bar plot, that this will make the bar plot automatically label those numbers with the proper names. So now we just use the bar plot command. The bar plot command first asks for what your two means are, or what all of the numbers are that you want bars of, and it makes bars of that height. You can also specify things like a main title, X label, a Y label. You can tell it what the Y limit is, so how high do you want the limit to be for your bars. In this case, it's always good practice to use whatever the actual scale was for your variable. So in this case, our variable our variable cycling score had an absolute minimum of 0 and an absolute maximum of 8. If you have a variable like that has an absolute min and max, make those your limits. If not, if you're using something that, if we were measuring like number of centimeters outside of the lane somebody drifted, that has an absolute minimum of 0. So we want that as our min. But it doesn't have an absolute max, so we could have used whatever like our max was plus a little bit just to make sure there's some space at the top. But when we have a real absolute min and max, we want to use them. So I also included the colors that I saved earlier. I could have saved these as a variable as well. I could have had like cycle.colors, and it could have been equal to a list of these colors. I didn't do that, but I just as well could have. Maybe I should have. But now I have my bar plot. All I need to do now is add error bars. For some reason, R doesn't have a handy command to just add error bars to a plot. So Ben wrote a command a couple of years ago, and then I touched it up a year or two ago to make it a little more flexible. But this is called the SE bar function. If you want to use this, if you want to generate a bar plot, just copy this function into your own R file, so into your own script, and you can run SE bar. So this is just a function we wrote. It's just a custom function that takes a few variables. It takes the condition of your first bar, or it takes the the name of your first bar, the name of your second bar. No, that's not true. Sorry. It takes the bar plot that you want to add error bars to as the first argument. As a second argument, it takes the means, so the list of means for each bar. So this, you could have many plot, you could have more than 2 conditions and use this SE bar function, as long as you supply the same number of means as you do standard deviations, and as long as your ends are all the same. So all it does is calculate the standard error for each condition by taking the standard deviation that you provide. So you're telling it the standard deviation, and you're telling it the n. And if you remember from the lecture about standard deviation and variance and standard error, that's your estimate for the standard deviation of the population. Standard error is standard deviation divided by the square root of n, divided by the square root of your sample size. So as long as your sample sizes are the same for each condition, you can just tell this SE bar function the name of your bar plot, the list of your means, the list of your standard deviations, and the sample size for each condition. I didn't write it flexible enough to use use conditions with different sample sizes. But anytime you're using a t-test or next week's test in ANOVA, you should have the same sample size for every condition, so that shouldn't get in your way. So like I said, this SE bar function requires that you give the name of your bar plot. So I do need to give my bar plot a name. I called it BR. You can call it bar plot. You can call it fun plot. You can call it cycling plot. You can call it Justin. You can call it whatever you want. I called it BR just because I'm just about to use it for one thing. I don't really need to remember this name. So I saved my bar plot as BR, and I'm telling the SE bar function, my bar plot is called BR. My means are this list, this cycle.mean list. My standard deviations are this other list, cycle.sd. And my sample size for each condition was 16. And it draws error bars for me. So that's just saying that this is one standard error in either direction. So one standard deviation of the population mean for the headphones condition. This is one standard error for the control condition. And all that is to say is I'm guessing the population mean. So what I'm plotting, these bars, are the sample means. So this is my sample mean for the control sample that I had. This is the sample mean for the headphone sample that I had. And this error bar is saying that I'm guessing the population mean is somewhere in this range. So the whole population of control, if I had a very large sample, if I sampled everyone on Earth cycling in the control condition, I would guess that the mean is somewhere in here. And likewise, if I sampled everyone in my population for the headphones condition, it would be in here. And maybe my population isn't everyone on Earth. It's like every UCD student who regularly cycles, or whatever else my parameters are for the for recruiting for this experiment. Is it mandatory to add a bar plot? It's not mandatory, but anytime you're reporting a statistical test, an inferential statistical test, it is good practice to visualize the results of any significant findings. So if you found a significant difference between means, you need to visualize that for your reader somehow, or it's at least good practice. As your grader for the assessment, if you don't visualize your findings to me and you had a significant finding, I'm going to take points off. I'm going to be unhappy that I didn't get a visualization. So if you're doing a t-test, I do want to see a bar plot visualizing the results of that t-test, as long as what you found was significant. Even if you found something insignificant, it's still good practice to show, here's where my error bars overlapped and here's what I observed. But you don't have to use exactly the methods of generating a bar plot that I showed here. If this was like tricky, if you didn't really get what was going on with some of the bar plot, we can talk more about it. But I do expect to see a bar plot for any t-test. So that's that. That's our visualization with error bars. That's a great way to visualize the difference between means. You might have some other way to visualize the difference though. I think Andy Field recommends a bar plot as well, but other sources might recommend different visualizations. So that's that. That is all the way through a t-test, from data cleaning to assumptions checking, to running the t-test, reporting the t-test, and visualizing the result. We'll see you next week for ANOVA. ANOVA is a lot like t-test, but for more than two groups. We need to plot above the bar to show significance. You can do that. I didn't hear. It's actually really annoying in R to do that. It's not so bad in ggplot to do that. But you'll see that in published papers a lot of the times, where there will be like a bracket with like a star to say like this was a significant difference. You don't need to do that because you're telling the reader anyway that this was a significant difference. If you have a good way of doing that, like if you're comfortable in ggplot, or if you know how to write a command to do that in R, go right ahead. That would look great. But I definitely don't require it for this class. And even as like a journal reviewer, I don't really require that because I think this visualization gets the point across that this population mean is higher than this population mean, that this bar is fully non-overlapping with that bar. So I think that significance is demonstrated even without doing that, but you can do that if you want to. Anyway, yep, I'll see you next week. We'll see you next week for ANOVA. Please feel free to keep any questions and comments coming to us by email or by the feedback form. And yeah, next week will actually be our last statistical test, as the week after that is our review before the quiz. So we're coming in for a landing, folks. We're coming in hot. See you next week. Thanks, everybody.